Hello, I'm Joe Vados. This video presents my artificial blood vessel benchmark project for an executive manufacturing audience. I use SolidWorks flow simulations to compare three common graph polymers, which include PTFE, PT, and polyurethane, and I test them across three graph lengths and two different flow conditions. The goal of this project was to translate simulation outcomes into a clear manufacturable product recommendation. Objective and decision question. So, the decision question here is which material and length combination should a manufacturer prioritize for safe, reliable artificial blood vessels? To answer that question, I simulated the three polymers that I mentioned before, PTFE, PT, and PU, at different lengths of 1 millimeter, 10 millimeters, and 100 millimeters under normal resting flow, and also at 5 times the normal rate, for that worst case scenario. I then compared maximum stress as well as strain to determine safety margins and deformation behavior that matter for real world performance and durability. Design inputs. To make the comparison fair, I held geometry and boundary conditions constant across every run. The only variables that would change were the wall material and graph length. The length tiers represent realistic clinical products, such as a very short 1 millimeter patch-like segment, a 10 millimeter connector or short graph region, and a 100 millimeter long graph segment. Each configuration was tested under two hemodynamic loads, so a normal flow baseline, which I had to research that number, and 5 times that number, for that worst case scenario representing extreme physiologic loading. So, simulation setups. All simulations were performed in SolidWorks with fluid structure interaction. Blood was modeled as a Newtonian fluid, so that differences in results were driven by vessel material mechanics rather than rheology assumptions. The inlet boundary was a specified volumetric flow rate for either normal or 5 times the conditions. The outlet was a physiologic pressure, and the lumen wall used no slit flow coupled to structural analysis. For each run, I recorded maximum von Mises stress and maximum equivalent strain to compare design on both load-bearing safety and deformation behavior. So this table summarizes the peak wall stress for every design under normal flow. Stresses were all below about 1.1 megapascals, indicating all three materials operate safely at baseline regardless of the length. However, under 5 times the flow, stresses increased dramatically as expected. The most important pattern is length driven. So the 1 millimeter segments produce the highest stress peaks around 14 to 15 megapascals across every material. The 10 millimeter segments dropped peak stress into roughly the 5.7 to 5.8 megapascal range. And then the 100 millimeter segments, the largest ones, showed the lowest peak stresses, about 3 to 3.4 megapascals. So short segments create localized stress concentrations, while longer segments distribute the load more smoothly along the graph, which makes more sense. The more length you have, the more weight and more stress can be supported. Besides stress, we also measured strain. So stress tells us whether the graph can survive load, but strain tells us how much it deforms over time. The key to compliance matching and long-term fatigue risk. So the strain results followed each material's stiffness. PTFE being the stiffest showed the smallest strains in every configuration. PET was in the middle, showing more deformation than PTFE, but less than polyurethane. And polyurethane showed the highest strain values in all cases, especially in the short segments under 5 times the normal flow rate, meaning it is the most compliant, but also the most prone to large deformations under extreme conditions. So, what does graph length do to performance? So, pulling stress and strain together, length is a major design driver. Very short graphs tend to concentrate both stress and strain near their boundaries because the loading and constraints change abruptly in the interfaces. That's why the 1 millimeter segments show the largest local peaks under that 5 times normal flow rate. Longer graphs spread the load over more wall area, lowering peak stress but also increasing total deformation along the length. From a manufacturing perspective, this means that short repair type products need extra attention to interface design and reinforcement at the endpoints. So, what are some of the trade offs? So, now the manufacturing relevant part, matching material to application. PTFE had the best resistance to deformation, giving low strain while handling high stresses. That makes it a strong candidate for high pressure, durability first grafts, especially in the larger arteries. PET stress performance tracked closely to PTFE, but its intermediate strain suggests a better compliance balance for longer segments where distributing load matters. Polyurethane showed slightly lower stress but much higher strain, which is useful for compliance matching in smaller or more flexible vessel regions, but it does raise concerns about creep or fatigue unless reinforced. Economically speaking, and for a regulatory standpoint, PTFE and PET currently offer the best balance of manufacturability, cost, and mechanical reliability, while polyurethane, on the other hand, is promising but would require more durability validation. So, final recommendations. So, based on these simulations, there's no single universal winner, I would say. Optimal design depends on the vessel environment and the product goal for a manufacturable portfolio. So, one, we have PTFE, which should be prioritized for high pressure, large artery grafts, and short to mid length products where low deformation and high durability are critical. For PET, it should be prioritized for medium pressure, longer graft segments where stress distribution is balanced and compliance matters. So for polyurethane, it should be positioned as a specialized compliance matching graft for smaller or more dynamic vessel regions, but only with fatigue mitigating reinforcement and further testing. On the length side, avoid unreinforced ultra short patches as standalone surge load products because they amplify stress at interfaces. So, with every project, there are limitations. So, here are the limitations. These results are a strong comparative baseline, but several simplifications limit direct clinical translation. Blood was treated as Newtonian, the vessel geometry was straight and uniform, and all materials were modeled as linearly elastic and isotropic. I also did not include cyclic fatigue or biological processes like thrombosis, remodeling, or endothelialization. These factors could shift absolute numbers, but the comparative trends across materials and lengths are still highly informative for early stage design decisions. So here are my references, but we could talk about some future work. So future work should add pulsatile fatigue, viscoelastic, and anisotropic material models, and more realistic geometries to refine product level predictions. But even with the current model, the bottom line guidance is clear. PTFE and PET form a robust manufacturable core product line, while polyurethane is a targeted compliance match option that needs durability engineering. Thanks for watching, and I'm happy to answer any questions about scaling these findings into production specs. Who knows? Maybe my work here might contribute in some way. Thank you.